Hello students, have you ever wondered why some objects float with only a part inside water, like an iceberg, while others float almost completely submerged, like a piece of wood? This mystery is explained by the relation between the volume of the submerged part of a body and the densities of both the liquid and the body. Today, we will dive into this fascinating principle step by step. Let's begin with the basics. Suppose we have a body of density ρs and its total volume is V. The weight of this body is given by W equals V into ρs into g, where ρs is the density of the solid and g is the acceleration due to gravity. This is the downward force acting through the center of gravity of the body. Now, when this body is placed in a liquid of density ρl, it displaces a certain volume V of liquid. The buoyant force, or upthrust, exerted by the liquid is Fp equals V into ρl into g, where V is the submerged volume of the body. This upward force acts through the center of buoyancy of the displaced liquid. For a body to float in equilibrium, its weight must equal the buoyant force. That means W equals Fb. Substituting the expressions, we get V into ρs into g equals V into ρl into g. Notice how g cancels out. What remains is the fundamental relation V by V equals ρs by ρl. This shows how the fraction of the body submerged depends directly on the ratio of the densities. Thus, the ratio of the submerged volume to the total volume of the body equals the ratio of the density of the body to the density of the liquid. This is a beautiful result because it tells us immediately how much of an object will remain underwater and how much will be above the surface. The lighter the body compared to the liquid, the smaller the submerged part. Let's take an example. A cork has density 3/4 grams per cubic centimeter, while water has density 1 gram per cubic centimeter. Using the formula V by V equals ρs by ρl, we get 3/4. That means 3/4 of the cork's volume is submerged, while 1/4 remains outside. That's why cork floats high on water. Another example is a cube of ice with density 0.9 grams per cubic centimeter. Since water has density 1 gram per cubic centimeter, the ratio V by V equals 0.9. That means 90% of the ice cube is underwater and only 10% is visible above the surface. This explains the real-world phenomenon of icebergs, where the majority of their volume is hidden beneath the ocean's surface. So to sum up, the fraction of a floating body submerged depends only on the ratio of its density to the density of the liquid. This principle beautifully explains why wood, cork, or ice floats the way they do. It is a direct outcome of Archimedes' principle and is used in shipbuilding, hydrometers, and even in understanding natural wonders like floating icebergs. I hope you now feel confident in explaining why some bodies float higher than others. See you in the next session with another amazing concept of physics.